Hello, everybody. Can you hear me? Can I get a thumbs up? Yes, great. Thank you for joining me this afternoon. This is CON302, Best Practices for Building Interactive Applications with AWS Lambda. My name is Benjamin Smith. I'm a Senior Developer Advocate on the serverless team. I'm actually based out of our London office in the UK. Random fact about me, I once taught David Hasselhoff to ski. If any of you don't know who he is, then good for you, fair enough. Really the most important piece of information on this particular slide is just my contact information. So if there's any questions over the next 60 minutes that I don't manage to cover that you're still left with, please do reach out with me either on Twitter or email. My information's just there for you. Okay, everything I talk about during this session, I hope will be in service to one of these 4 fundamental goals. I want to help you to give more value to your customers by using serverless technologies. I want to help you make your applications more reliable and more resilient to faults and failures. And of course, to be able to have them scale as efficiently as possible. And to be able to do this as quickly as possible using AWS Lambda and other serverless technologies. So this is what I'm going to cover over the next 60 minutes. First, we'll talk about why developers are using serverless in production today. And I actually want to show you some of the things that developers are saying about serverless applications. Then we'll talk about the difference between synchronous and asynchronous workloads, what it means to invoke Lambda synchronously, what it means to invoke Lambda asynchronously, when you might choose one invocation pattern over the other. And we'll also talk about, of course, interactive Lambda applications, what you can do with an interactive Lambda application, what I mean when I define an interactive Lambda application. Then we'll spend quite a lot of time talking about a brand new way of invoking your Lambda functions. There was a new thing launched about 10 days ago that allows more simple access to your Lambda functions, and I'll spend some time talking about that. And then we'll talk about some best practices for optimizing cold starts with Lambda. Okay, so why do developers use serverless technology? About a year ago, I was tasked with building a brand new series of getting started content for serverless. And this was content aimed at developers who are already building things, but maybe completely new to serverless technologies. So the first thing I did was to reach out to the serverless community on Twitter and to just ask, why are you using serverless technologies? What were some of the tough things to get your head around when you first started building with serverless? And the reason I put the QR code up here with this link is because this tweet got well over 100 comments. And these are comments by people who are all quite far along on their serverless journey. So I think they're really useful people to follow that are using serverless in production. I just wanted to share 2 or 3 of the responses because it's slightly different to the messaging that you might hear people at AWS speak about. So this person says serverless is not worrying about anything other than code and the billing. They found it hard to get their head around that Lambda is actually fast, massively parallel, and they say terrible with state management. Okay. This person says, I have to deal with servers less, but I have to deal with YAML deployment scripts more. Another one here, I do not have to provision and maintain servers, but difficult estimating costs in advance, difficult understanding that it's not more widely adopted. Developing global enterprise scale apps with ease, difficult convincing stakeholders that an app doesn't have to be 100% serverless. Like I said, there's well over 100 responses to this. So if you're interested in following people on Twitter who are using serverless every day actively in production, then do follow this tweet. Broadly though, each one of the responses can be summarized with one of these 3 categories, right? Developers are saying they don't want to pay when my workload is idle. And this is a fundamental principle of serverless technology. You pay per use. If you're not using the service, you don't pay for it. Another one here, I only want to write business logic. So you might have heard the term used by an AWS employee of undifferentiated heavy lifting before. This is referring to things like patching, securing, scaling, all the things that you need to do with your infrastructure before you can even start writing code. With serverless technologies, there's a whole team of people at AWS and a whole range of services and infrastructure that manages all of that for you, such that all you need to do is concentrate on the business logic, the part of your application which differentiates you from other applications. The third thing here is I want my application to scale on its own, which of course is another really important part of serverless technologies. Now, I think a nice way of explaining why serverless technologies is able to scale so efficiently and so agile is to look at the difference between vertical scaling and horizontal scaling. Now, traditional applications scale more vertically. Here's a nice analogy to kind of imagine that. Imagine at the end of the summit here, you decide to go for dinner, and you decide to rent one of these lovely electric bikes in town to get yourself there. And on the way to pick up a bike, you bump into some friends that you meet in the audience here, and you decide you're going to go together. Well, bike's not big enough to carry all three of you now, so you decide you're going to take a taxi. Then on the way to the taxi rank, you bump into someone else. Taxi's no longer big enough. You're going to have to scale up and get a bus or a bigger car. The point is that each increase in load requires the purchase of a larger transport mode to bear that load. That's an example, a loose example of vertical scaling. Now, if you apply this same analogy to horizontal scaling, you can see exactly how it works just by this imagery, right? With horizontal scaling, you add an additional capacity unit in line with demand. So how does this apply to compute and to serverless? Well, another way of looking at it is in terms of capacity, and that's capacity used and unused. Let's say we're going to really simplify our application here, and we have a machine running that we're renting, say, on a monthly, weekly, hourly basis. And that machine has a certain amount of capacity to handle requests. And as your application becomes more widely used, you kind of get more traffic and you're using up more capacity. Now you'll have a buffer. You've over-provisioned your server because you know that you need to have that buffer in case you get more traffic. But at a certain point, you're going to have to clone that machine, you're going to have to scale up, you're going to have to clone the code on it, the infrastructure behind it, and you're going to have to provision again. And you're going to have to maintain that buffer again. And at some point, you'll have to go through the same process. Now, each time here, you're always paying for this unused capacity, right? Because you always need this to extend into. With serverless and horizontal scaling, each Lambda function executes in response to each individual event. If you have multiple requests to a Lambda function, you have multiple instances of that function executing. It scales in line with demand directly. Once that function's finished running, it shuts down, and that execution environment will eventually become available for another function. The final thing I just wanted to draw attention to here is when you go to build an application using serverless technologies, all you really need to think about is what runtime you're going to go ahead and start building with. Whereas with a more traditional application, you need to think about provisioning servers. Maybe you need to raise a ticket in order to do that. Someone needs to maintain those servers. You need to configure load balancing of traffic to those machines. You need to configure network access. You need to configure backups, resource systems. You need to make sure it's secure, the runtime is patched and updated. You get the point. With serverless, you just need to choose which language you're going to go ahead and build with. Okay, so this is a talk about AWS-based applications, more specifically, interactive Lambda applications. Now, what's an interactive Lambda application? It's a Lambda function where that function is invoked using an HTTP request, and therefore it will return an HTTP response. So this is what I mean when I'm talking about an interactive Lambda application. So let's just quickly make sure we're all talking about the same thing when we talk about an interactive Lambda application being synchronous, okay? When you send an HTTP request and receive an HTTP response, you're running a synchronous command. Synchronous command looks a little bit like this, where you have a client or a requester that sends a request to service A. Service A might send that request downstream to service B. Service B will run what it has to run, return back to service A, and then service A will eventually return a response back to the client. That's a synchronous command-driven workload. If I run that same command in an asynchronous mode, it looks more like this. Client sends a request to service A sends back an acknowledgement right away. It then sends on downstream to service B, and you'll notice service B doesn't send any response back to the client. Key difference here can be represented by this lovely pink dotted line. So this represents the amount of time that our client is waiting to hear a response back from that service A. Okay? In the synchronous mode, it's waiting a lot longer because it needs to hear back the actual result. In the asynchronous mode, it just gets an acknowledgement back. And this is important because this time is blocking time. Our client can't move on to the next procedure until it's received that response. So you can invoke Lambda with a few different modes. You can invoke Lambda synchronously, asynchronously, and there's actually a third invocation type called event source mapping, which is slightly out of scope for this particular talk, but that's about polling and streaming. We're going to focus on synchronous and asynchronous Lambda invocations. So you should invoke Lambda synchronously when the caller expects a response from your function. And you should invoke Lambda asynchronously when the caller doesn't expect a response. Here's what that looks like under the hood. So it's important to know that there's a difference between the Lambda service and a Lambda function. The Lambda service is what runs your Lambda functions, okay? So when you invoke Lambda synchronously, for example, via a URL endpoint from API Gateway, it looks a little bit like this. You send your request in, your HTTP request to API Gateway. API Gateway proxies that on to the Lambda service, and the first thing it sends it to is called the Lambda front-end API. And this is a microservice inside of Lambda. The front-end API will then do a bunch of things, but one of the things that it will do is it will know the location of an execution environment that it will run your Lambda code in. And it will go ahead, run your Lambda code, wait around for the response or for an error, and return either of those two things back to API Gateway, who returns that back to the requester. If I do the same workload, but invoke Lambda asynchronously, let's say from a service like Amazon Event Bridge. Amazon Event Bridge, something goes onto my event bus, a rule in Amazon Event Bridge routes that down to my Lambda function. First thing it hits again is this front-end API. Front-end API then sends back an acknowledgement that it's received a request to invoke Lambda. It then also puts that request onto an internal queue. Now, this is a queue not visible to you, not visible to anyone outside of AWS. It's managed by the service. And the request can sit on this queue for up to 6 hours, and it will then invoke your function on your behalf. If the function fails, it goes back onto the queue up to 2 times, so three invocation tries in total. If it fails after that 3rd time, then you can configure Lambda to send that invocation request downstream to a dead letter queue or some other destination. So when should you choose to invoke Lambda synchronously or asynchronously? Just one question really that typically you can ask yourself when you're building your applications, and that is, do I need to wait for a result? And if you do, you can use a synchronous workload or synchronous invocation, and if you don't, then you can use an asynchronous invocation. Now, here's where it gets a little bit complicated. You can go ahead and invoke Lambda synchronously via a request from something like API Gateway, and then you can have your Lambda function kick off asynchronous background workloads. For example, I could have my Lambda function kick off a AWS step functions workflow. Now, step functions workflow can run for up to 1 year, so Lambda's not going to hang around waiting for the response. It will just return the acknowledgement that the workflow started. Similarly, I can, inside of Lambda, run a request to call out to some external API. For example, I can call out and post a message on Slack. That's an asynchronous request. An asynchronous request triggered from a synchronous Lambda invocation. So, what can you make with an interactive Lambda application? Pretty much anything, actually. Here's a random list of stuff, but I could have just kept going. We're going to cover connecting 2 applications together in a minute. I'll talk about that in a bit more detail. But you can do things like extending applications. Remember, one of the Twitter responses was someone being surprised that you can just add a serverless piece to a non-serverless application. Well, this could be extending an existing on-prem application or a SaaS application just by adding a serverless workload to it. You can kick off asynchronous workloads. You can do things like machine learning inferencing. You can build web applications, web backends, data processing, chatbots. Alexa skills, of course, is a huge use case for Lambda. It's the first thing I ever did when I was building with Lambda. We'll just look quickly at this example use case of connecting two applications together. Now, this actually forms the basis of a whole series of getting started content that was triggered by that initial tweet, actually. So what this application does is it connects GitHub to Slack, such that whenever somebody stars a repository in GitHub, it sends a payload to my Lambda function. My Lambda function transforms that payload and sends it onto my Slack channel. This is the result in my Slack channel. It says, hey, there's been a new GitHub star. You now have 10 stars, and the star was made by this person. And like I say, this forms the whole series of blog content, tutorials, and GitHub sample code that you can use to try and make this application from scratch if you're interested. This is that application in motion, right? So on the left is Slack, and on the right is my GitHub repository. And my cursor here, I move it up to the star icon. I favorite my GitHub repo. And within a second or two, I get my message in Slack saying, hey, someone's just starred your repo. It's now got 37 stars or whatever it says there. Really simple little webhook example of connecting two apps together using a Lambda function. So what actually just happened? How did that work? Where's the business logic? The business logic is loosely referred to as code, but really it's not just code. It's about doing something to some data to produce a valuable output. That's your business logic. And with Lambda, something that doesn't change is this concept of input, process, and output. I still need an input for my Lambda function. It still has to run a transform or some sort of compute, some process on that input, and it still has to return some sort of output. So let's quickly look at what the input, the process, and the output was for that little application that I just showed you. This is the input sent by Slack to my Lambda function. And it's just a JSON payload that contains useful things like the name of the repository, the amount of stars on that repository, and the name of the person that did the action. This is posted with an HTTP post request to my Lambda function. This is my Lambda function code for this particular app. You can see at the top line says exports.handler. Now this is a Lambda function written in Node.js, one of the supported runtimes. And this is my handler function. The handler function is the part of your Lambda function that tells the Lambda service where to start running your code. Okay, that's the handler function. And you can see there's an object handed to this handler function, which I've called event. And this object is just this input payload, right? It's exactly what it is. And I reference that object in the process, the next part of my Lambda function. I'm creating a const called message, and I'm putting some text in there, and I'm grabbing the name of the repository, and I'll grab some other things like the number of stars and stuff like that. Then I'm using a node module called Axios, which is for sending HTTP requests, and I'm using that to post this to a Slack URL, which puts it onto my Slack channel. And it's really just 5 or 6 lines of code to do this. And then the output here is my return statement of the acknowledgement that it's been sent to Slack. So Lambda is still using input, process, and output. The bit I've missed out, how did the event payload get from GitHub to Lambda? How did I tell GitHub a URL to post some information to my Lambda function? Well, anyone who's built any kind of a web app with Lambda will probably have guessed that I use this service called Amazon API Gateway. So API Gateway is this really comprehensive service for building APIs at almost any scale to create a URL which acts as a front door to your AWS services, okay? And this works great. You can see it works great. But customers have been looking for a year or two now for new ways to simplify the number of steps that it takes to access business logic in their Lambda functions. Customers wanted an easier way to access their Lambda functions and invoke it, an easier way to generate a URL. And about 10 days ago, we launched this brand new part of Lambda called Lambda Function URLs. So this is a brand new simple way to invoke your Lambda function synchronously with an HTTP request. I'm going to spend a bit of time going into this now. This is what your Lambda function URL looks like. So it's always HTTPS. It's a uniquely generated ID. .lambda URL, and then the region that you generated your function in, and then it will say .on.aws. Now, function URLs is actually part of the Lambda service. It's not an additional service. It's not part of API Gateway or anything new. It's built into Lambda. It's actually a separate resource block in CloudFormation. And we know now that it generates a URL to invoke my Lambda function. You can point this URL to the latest alias or a user-defined alias on your function. So for my little example app here, my little webhook app, a great way of simplifying this would be to replace API Gateway with a function URL. And then I've moved out whole service and I'm invoking my Lambda function directly. So how do you create a Lambda function URL? Pretty much from anywhere you would expect, to be honest, from the management console, using the CLI, using templating languages like SAM or CloudFormation or CDK, or any number of third-party templating languages, for example, serverless template language. How do I then invoke my Lambda function using a function URL? Well, from anywhere that I can send an HTTP request. So from my browser, from a curl request, from Postman, or even programmatically, I can invoke my Lambda function now. This is the kind of steps that I would use to create a function URL from within the console. I go to the Lambda function console, I click on the Create Function button, and you scroll down to this Advanced Settings drop-down, and hidden down there is this little checkbox that says Enable Function URL. I get some more options once I hit that checkbox, which I'll go into them in just a moment. Then, as soon as my function is created, in the top right-hand corner of the function page is this brand new function URL, and I can click directly on that and invoke my function directly in the browser. So I mentioned there were some options once you select to create a function URL. The first important option is the authorization type. There's two types of authorization that you can set on your function URL. There's I am authorization, and there's no authorization. There's actually a third that you could try, which is to roll your own in code. So this would be similar to using a Lambda authorizer with API Gateway. So if you wanted to authorize with something like Auth0 or Cognito, or some other API key that you have, you can build that into your function code if you like. So if I want to protect who's able to invoke my function using this URL, or who's able to create a function URL, there's a bunch of actions that are now new and available in order for me to do that. So there's one called create function URL config, there's update function config, delete, get, and list function config. These all control who's able to interact with function URLs. Then there's one called invoke function URL, this one here. So this is the action you need to apply to your Lambda function URL if you have I am authorization turned on. And you add this action to a user, an I am user or an I am role. So this is an I am role that allows me to invoke my function using a function URL on this particular Lambda function on the dev alias. That's quite long-winded, I know. Then, once I've done that, I can send a request to that URL, and in the header, I need to put a SIGv4 signed request, right? A SIGv4 signed request, which tells the Lambda service that I'm the person assigned to that role here. How do I create a SIGv4 signed request? Well, I go into the IAM console, I grab the access key and the access key ID associated with that role or that user, and then I will add this SIGv4 sign request to the header of my HTTP request. Now, stay with me here, because the first time I discovered this is how you do it, I thought it was a bit mad, but this is how you do it manually. First, you have to create a signing key. Then you have to create a canonical request. You use that canonical request in the string to sign, and you put them together, and you hash that, and you add that to the header of your function URL request. Now, don't panic. You don't really have to do all that manually. Pretty much any runtime, any library, any package that you're using to build your applications has a method or a library built in to enable you to create SIGv4 sign requests. So you shouldn't have to go through all those hoops to create that manually, but you could if you wanted to. Similarly here, if I wanted to test my function URLs using something like Postman, then Postman actually has an authorization type called AWS secret And here I just paste in my secret key and my secret key ID, and it generates a SIG-v4 sign request for me. Who here has ever seen an error like this, a cause error, when building? A lot of hands went up really quick. Good, it's not just me. Cause error, cross-origin resource sharing. If you want to invoke, or if you want to send a request to a URL from a different domain other than that URL in the browser will often do a pre-flight request to check if you're allowed to invoke that URL or request that URL. Now, every time I think I've figured out how cores work and how to get over it, I come back to a new project a couple months later and start all over again. Really complicated thing for me. My good friend and colleague, Eric Johnson, he's a real big fan of cores. This is his favorite quote. If cores had a face, I'd punch it in the nose. And I think he's spot on. Well, good news, with function URLs, cores should be much easier. You should be able to get past this now. You're actually able to configure cores in the configuration of your function URL, right, in an editable form. Actually, this is what that looks like. So you tick this box when you create your function URL that says configure cores. And then on the right here, you can see the options that you're able to input into a form to set all the things necessary for the response, things like the allow headers and the allow methods. I'll just hold on that page. I can see some people taking pictures of it. OK. These are the things that you're able to configure in that editable form, right? So this is everything you need to configure cores. The origin, the method, the max age, all nicely available to you. Now, if I want to create my own cores response, I can actually roll my own in my function code. So here, I'm returning my own headers that I want. I'm not configuring it using that form. I'm already comfortable with cores, and I'm just returning the response I want. So you can override it as well. So this is a SAM template, my favorite language for creating serverless applications. And at the top, I'm defining my Lambda function, the code URI, the handler, and all that stuff. And there's this new block called function URL config. And this is what's telling that this Lambda function should have its own function URL to go with it. I'm setting the auth type to 0, and I'm configuring the cores inside that as well. Same thing with CDK. I'm not going to walk through every line on this, there's quite a few, but essentially the point is you can configure cores and everything about your function URL in all the templating languages as well. It doesn't have to be in the console. This is the first thing I wanted to know when I started playing around with function URLs, is how do I interact with the paths, the methods, the query string parameters. If I invoke my function from a function URL and have a bunch of things after the slash, does that still invoke my function? How does that work? Well, I'll show you. This is an example of what the input payload looks like to Lambda when you invoke Lambda using a function URL. And this matches, I believe, it's identical to HTTP APIs from API Gateway. So you should be able to transition across the two relatively easily. So let's say I invoke my Lambda function from this path. I've got my function URL, and I have /mountain /Japan/Hokkaido. Now, if I want to access that path in my function code, here's how I do it. So here's my function handler, and you can see that that path is available to me in event.rawPath, right? That's my input. If I want to grab the HTTP method, get, post, patch, delete, etc., well, that's available to me in event.http.method. Query string parameters, this is everything after the question mark. These are slightly different, but still pretty easy to get to. So let's say I invoke my function with question mark mountain equals Mount Yote. Now, this will create a kind of key value pair where mountain is the key and Mount Yote is the value inside a block called query string parameters. So here I can access Mount Yote value from event.queryStringParameters.mountain. Okay, a couple more things that you should know about function URLs. That was the input payload. The response payload does some clever things for you too. it actually infers some stuff on the response payload. So things like the status code is added for you, the content type is set for you, anything that you return is actually put into the body of the response, and it by default sets it as base 64 encoded is false. What that means is if on the left here is my app.js, my exports, my function handler, and I just return a string that says hello world. What's actually returned in my HTTP response is this status code 200, hello world gets put into the body, there's a header added for me, base 64 false. So it's inferred a lot of that information for me, so it's a nice tidy response. If I returned a block that says message is hello world, well that's just put into the body for me as well. Sorry, I'm standing in the way, aren't I? I can override that as well, by the way. So if I set my own status code to 201, for example, then anything I put is actually overridden, so it doesn't infer anything for me in that instance. There's some new CloudWatch metrics that are available with function URLs. So you can get the sum of the request count, you can get the 4x and 5x error sum, and you can get the URL latency average and max. This is the really important part, right? Function URLs, because it's part of the Lambda service, it shares its limits with Lambda. It's not an additional service. So what that means is it gives you the same 6 megabytes response and request payload size as Lambda. It has a default 1000 up to tens of thousands TPS. It has a 15-minute timeout. Now this is brand new, a 15-minute timeout on your function URL as opposed to API Gateway's 29 seconds. There's no additional cost for invoking Lambda using a function URL. It's free access to your business logic. There's no additional cost. You still pay for the amount of time that your function runs, just like normal, down to the single-digit millisecond, but you don't pay to access your function. There's no additional timeout limits. It's the 15 minutes that Lambda offers, and there's no additional payload limits. So what kind of use cases does function URL kind of open up now? Well, I like this simple webhook use case where you just have a quick and simple invocation of a Lambda function, connect one thing to another. A great use of serverless, great use of Lambda in my opinion. It also opens up some other things as well, right? Think about this idea of free access to your business logic or free access to your stack essentially. Something like a fan-out request response model. Let's say I send a payload into Lambda. That Lambda function then puts something onto an Amazon SNS topic, which fans out to multiple other Lambda functions for something like image resizing. Now, these can be all done concurrently, nice and quickly, parallel processing, right? And that initial Lambda function can just return an acknowledgement back to me. Remember, I said you can send a synchronous invocation to Lambda and trigger asynchronous workloads. Well, this is a great example of that with free access to that Lambda function. Here's another one, high volume data ingestion. Again, using that 15-minute timeout and that free access to your business logic, you can send a request to Lambda, which could perhaps be forwarded on to Amazon Kinesis. That can stream something into S3, which you could analyze in Amazon QuickSight. You could add resiliency to this by adding a DLQ to your Lambda function. Another use case goes along with what we've been hearing from customers a lot, that they've been looking for simple ways to process big data workloads with Lambda. This is actually something that we've been working on for a number of years now, making it easier for customers to do big data workloads in Lambda. Back in 2017, we doubled the memory capacity of Lambda. 2018, we added 15-minute timeouts to Lambda, up from the 5 minutes previously. There was provision concurrency in 2019, elastic file system support in 2020, up to 10 gig of memory also in 2020, and container image support for your Lambda functions. So you can have package deployment sizes of up to 10 gigabytes at that point. Then about a month ago, we launched functions with up to 10 gigabytes of ephemeral temp storage. So the temp directory now can go up to 10 gigabytes. So Lambda in 2019 looks a lot different to Lambda today in terms of its storage and sort of package deployment limits. Your memory is 10 gigabytes, your ephemeral temp space is 10 gig, and your deployment package size is 10 gigabytes as well. So this makes Lambda a really appealing use case now for things like machine learning inferencing. where you can send your payload into Lambda. You can fetch your machine learning models and frameworks from an object store like S3, and then use that 15-minute timeout and that 10 GB ephemeral storage to run your machine learning inferencing on it. Another use case that we're already starting to see, and maybe some of the serverless purists will need to look away here, is running your entire website in a single Lambda function. People are doing this, and it's an interesting way to use function URLs. Because you can invoke Lambda with anything after that slash, anything from that URL, you can then set in your Lambda function code kind of router to route to the necessary piece of code internally based on the path and the method, right? A bit like a traditional MVC framework on PHP or an Express app. What you can then do is you can put something like Amazon CloudFront. Now, CloudFront is a CDN, content delivery network, with nodes all over the world that cache data closer to your users, making it a nicer, quicker, less latent experience. And you can put CloudFront in front of your function URL, generate your own custom domain, so that way you don't have to use the generated Lambda URL, you can create your own domain. Then you can create origins and rules to route to different origins. So Lambda's really good, and a really good billing model for running compute down to the single-digit milliseconds, right? You pay for the single-digit millisecond that a Lambda function is executing for. It's not very good at serving static assets that don't require any compute, things like JS files, images, CSS files. There's other services that are better than, for that, things like S3. So store your static files in S3, have them under a root, for example, /assets, and then use a rule in CloudFront to route everything for a static asset to S3 and everything for a dynamic compute to AWS Lambda. This way, you're becoming more and more serverless, using the services for the thing that they're most required. Okay, so you're building these interactive Lambda applications. They are using a synchronous request response model. You want to optimize them to run as quickly as possible, minimum latency. How do you do that? This is what I'm going to talk about for the next 20 minutes or so. So when you invoke a Lambda function, the first time that Lambda function is invoked, or if it hasn't been invoked for a while, it goes through 3 specific phases. This is the init phase, the invoke phase, and the shutdown phase, which is not on this slide here. Now, the init phase has some kind of some other tasks involved in it, right? The first thing the init phase does is it has to create a new execution environment, a new micro VM to run your function code inside. Then it has to grab your function code, whether you've put that as a zip file or a container image. It has to grab that and unpack that into this new execution environment. Then it has to initialize the runtime that you've configured for it, whether that's Node or Java or whatever you've set. Finally, it will start running the pre-handler initialization code. So this is everything that you've set above the function handler, things like packages and dependencies that you've brought in, global variables, database connections that you've set. That's everything that happens before it even invokes your function handler. And that's what you might have heard referred to as a cold start, right? Then a warm start is when all of that's already done and already set up, and it just invokes your function handler. Now, everything on the left-hand side of that pink line is what AWS is constantly working on to speed up and improve and optimize. Everything on the right-hand side, there's things that you can do and you have control of to optimize and improve. It's this really interesting thing where cold starts are not good for you, the customer, because it means your function takes longer to run. But they're also not good for the AWS, the business, because we take the cost of that, and there's more actions involved to get your function ready. So there's this interesting kind of syncopathy where we're both needing the same thing to happen, right? Both needing to reduce cold starts. So that's why there's a lot of effort going in all the time to try and find better ways to reduce this cold start issue. So what can you do to optimize for cold starts? How can you reduce that? One really quick win that's kind of easy to implement is to not just require the entire AWS SDK library. We see people doing this a lot where they think, I'm going to use the SDK, I'll pull in the whole thing, and maybe all they needed in their function was a particular client for DynamoDB, for example. In this instance here, me using this one DynamoDB client instead of the entire SDK, it speeds up my cold start time by 125 milliseconds. Even if I am using, for example, here the X-Ray SDK, I can modularize that even more by using a specific part of the SDK X-Ray core, and that speeds up my function cold start by 5 milliseconds. Did you know that the AWS SDK version 3 is a much smaller package size than version 2? So you should use version 3. It's much more modular. That will speed up your cold start deployment size by a great deal as well. So when does a cold start happen? Basically, it happens every time a new execution environment is needed to be spun up in response to an event. So this is when I'm scaling up my functions, when I set some provision concurrency, maybe when I update my code, if an environment is refreshed, maybe there's an actual failure in the underlying resources, or the service is rebalancing across zones. There's lots of different reasons when I might need a new execution environment for my Lambda function. Actually, cold starts, I just want to point out, are less of a deal than perhaps they used to be. They only occur in 1% of all Lambda invocations, less than 1%. And when they do occur, they're typically less than 100 milliseconds, sometimes more than a second, depending on what you've got in your function code. I think it's useful to understand concurrency to understand how you can help reduce this cold start issue and why these cold start issues are happening, right? So concurrency is the number of requests that your function is serving, your one function is serving at any given time. And each Lambda execution environment can only run one single event at a time. So this is what it looks like. Let's say I have a brand new function or a function that hasn't been invoked for a long time, and I get a request to invoke that function. It goes through that init cold start phase that we looked at before, and then finally it can invoke my function code, right? This is where my execution environment is, and this is blocked until the invocation has finished. Nothing else can run in this until it's finished running my invocation. So let's say a couple milliseconds later, I get 2 more brand new requests to this same function. Well, they need to spin up a brand new execution environment each, because the first execution environment is already being used. Let's say I get 2 more requests. So now I have 5 concurrent requests running all at the same time. But this pink line here shows that, okay, request number 1 has finished running. So that execution environment is now warm. It's already gone through the cold start phase, already has my runtime ready and my code ready and my dependencies package ready to go. There's a free execution environment. So that means the next request that comes in will go straight into that environment, and it doesn't have to go through the cold start. This is what's known as a warm start. And so on and so forth. These are the cold start, warm start lifecycle. Your execution environment will hang around for a period of time, waiting just in case it's needed for another invocation for a warm start. And this is how you count the concurrency. You can literally draw a line down the middle, and here you can see the different executions that are running concurrently. Okay, so just to kind of summarize this section, the point is, don't load into your function things that you don't need inside your function. Try not to be too lazy about this. Import only the things you need. And try and optimize all the dependencies that you're going to use as well. It can help even to kind of minify your code. Avoid creating these huge monolithic Lambda functions if you can. Remember I said that execution environment hangs around, waiting for a new invocation. Well, when it hangs around, all the global environments that you've declared in the previous execution, they hang around too, right? So any constants or any kind of environment variables or any code variables that you need that might be used as global, you can declare them above the function handler, and you don't need to redeclare them. That's another way to help optimize. You do have to be a bit careful with this. Don't declare anything that's kind of secret or sensitive. Don't put any passwords above your function handler, obviously. The other thing is you can define your database connections above the function handler as well, so they hang around, but you manage them inside the function handler code to keep them alive. Are there any Java developers sitting in the audience here? Okay, this slide is for you guys, specifically. We published a blog post about 2 weeks ago, which showed how you can reduce cold start times for functions running in Java by up to 60%. And this really works, okay? All you have to do to enable this is to add this funny looking environment variable. It's just a config change, just add this environment variable. What this does is it changes the JVM, the tiered compilation of the JVM to stop at tier level 1, which is what most functions require when they're running in Java. So you do this, we've examined this, we've checked it before we published our blog post. It will cut down your cold start time significantly just by adding this one environment variable. And there's lots of different little tips and tricks you can do for different managed runtimes, right? So look around out there, specific to your function's workload, your function's code, what kind of configuration changes can you make to make your function run more performantly? Okay, I've spoken a lot about function URLs here, but there's other ways to synchronously invoke Lambda, right? And they're not going away, so I don't want to leave them out. Amazon API Gateway, REST APIs, that's still a huge thing. Application load balancer, also a great way of invoking Lambda synchronously. Remember, the synchronous invocation is an interactive Lambda application. Just want to compare and contrast across the three here. So you have this thing called ALB. This is Application Load Balancer. And this allows you to send HTTPS and HTTP requests to something called a target group. Now, a target group can be a collection of EC2 instances or an individual Lambda function. Then you define a listener to route your HTTP request to a target group based on things like the path, the method, and the protocol. ALB also has something called health checks, which pings these target groups for you on a regular basis to make sure they're healthy and alive. And if they fail, then you can set up rules to handle that accordingly. So if I wanted to build an application with ALB, probably my first group is already a collection of EC2 instances, and my listener could be based on a port and protocol of port 80, for example. And let's say I want to add a serverless component to this application. Well, that's my first Lambda function, and I can just say anything on /order, which is this order processing part of my application. I want to route to this Lambda function. Maybe then I want to add an API to my application. I can say anything that /API route to this Lambda function, and so on and so forth. You can start to add serverless components to your EC2 app, or start to kind of migrate away from EC2 and into serverless without changing too much about how your application works. Okay, API Gateway. API Gateway lets you create and manage REST and WebSocket APIs that run at almost any scale. It supports this thing called VTL, Velocity Templating Language. And this allows you to transform the input and output payloads before they get sent downstream to the next service. And you do that in API Gateway configuration. You don't do that in a Lambda function or in any other code. It supports parameter and payload validation. Now, this has multiple authorization options with things like Cognito, API keys, custom Lambda authorizers, way more than something like function URLs. This is what I think makes API Gateway the most powerful thing, is that it natively integrates with over 100 other AWS services. So you can go from API Gateway to another service without anything in between, right? Directly giving you access to your AWS stack. So here's how you might build an application with API Gateway at the front. I might have a URL endpoint that's GET, which might allow me to fetch something directly from my DynamoDB database using VTL to transform that request and set that request up in a way that DynamoDB likes. I might have something that's /order or post order, and this could trigger step functions workflow. It could trigger an express workflow and hang around and wait for that step functions response, return that directly from the HTTP response. And then I might use another part of my API Gateway to configure routes to build an entire REST API, which is authenticated using something like Cognito, for example. Here's my best guess at how to kind of split these up, right? So you have Amazon API Gateway REST APIs. That doesn't support HTTP. Function URLs does not support HTTP, Application Load Balancer does. All three of them support HTTPS. In terms of authorization, Function URLs has IAM authorization that you can configure, and you can also roll your own in custom code in your Lambda function. API Gateway has a whole plethora of authorization options. Same can't be said for Application Load Balancer. When used with Lambda, all three have this 6 megabytes payload limit. Now, this is where it gets interesting. The max timeout for API Gateway is 29 seconds. Max timeout when you use ALB or function URLs is 15 minutes. This is a huge difference point, right? Big point of distinction. API Gateway has this feature that allows you to generate an entire SDK that you can hand on to your developer teams to interact with your API. Hugely undersold, in my opinion. The cost is the other huge differentiator here. So API Gateway costs $3.50 per million for the first 330 million. Application Load Balancer, you pay hourly plus capacity units, so maybe not strictly serverless in that sense. Function URLs, as I said before, is completely free to access your Lambda function. And then finally, API Gateway and Application Load Balancer works well and is compatible with AWS WAF, whereas Function URLs is not. So this is what I suggest you use the 3 for. Feel free to do this differently. Okay, so API Gateway REST API is great for using these built-in service integrations. Go directly from a URL to a service without needing any compute or any transform. Great for reducing code because you're not creating loads of Lambda functions unnecessarily. Ideal for REST APIs and ideal for added security with all those different authorization options. Application Load Balancer, perfect for hybrid applications, applications that are already on EC2, already using ALB, where you need to migrate towards serverless. And then you have function URLs, great for getting started with Lambda, great for simple invocations of your Lambda functions, already seeing people use it for things like web applications and longer running workloads like machine learning inferencing, and free access to your business logic. So to recap everything we've talked about, I would suggest you use an asynchronous workload, invoke Lambda asynchronously where you can if you don't need a response from your Lambda function. In terms of optimizing your function for cold starts, initialize all your resources outside of the function handler, above the function handler. Try to minimize the deployment package size as well. Keep that as small as possible. Then we talked about AWS Lambda having this new ephemeral storage limit of up to 10 gigs. And we spent quite a lot of time talking about this brand new thing launched recently called function URLs, a simple way to invoke a Lambda function via an HTTP request. Now, if you do have any questions about anything I've spoken today or anything to do with serverless, I'm going to be on the Serverless Espresso booth for the rest of the afternoon, the next hour or two. Everything on Serverless Espresso has been built using these services with best practices as much as possible. I'll be happy to talk to you about that or about anything else serverless. And that's it. Thank you very much. I hope you enjoy the rest of your time here in San Francisco. Thank you.